Hi guys, this is Dr. J here, and in this video I'm going to give you a basic introduction to solutions. So solutions is a very common term in chemistry, okay, and most of you are already familiar with what are solutions even though you may not know how to define it technically. Okay, so in chemistry we define solutions as homogeneous mixtures of two or more substances. Okay, so a homogeneous mixture that has two or more substances are usually called solutions. Okay, so basically, uh, the first thing that you need to know is what is homogeneous. What is the meaning of the term homogeneous, right? So basically, homogeneous means evenly distributed. So when you have a mixture of two components or two substances, you have to have a evenly distributed mixture in order to have a solution. And then usually these two components should have sufficient attractions between them. Okay, sufficient attractions between them. And also, when you have two components to a mixture, these two components could be identified as the solute and solvent. Okay, the solute and the solvent. So in a solution, you can only have one solvent, but you could have more than one solute. Okay, so in a solution, you have two components. You have two components, solutes and a solvent. Okay, but in a solution, you can only have one solvent, but of course, you can have more than one solute. More than one solute. Okay. How do you separate the solute from a solvent? That is the next question that you should have, right? So basically, a solvent is present in a solution in much larger amounts, okay, as compared to solutes. So basically, quantity wise, you have more solvent as compared to solutes. As compared to solutes. So let's take an example. Let's say you go and buy an alcohol bottle. Okay, so let's say it's a 40% by volume alcohol bottle. Okay, so you are buying a 40% by volume alcohol bottle, which means you have 40% ethanol. Okay, by volume you have 40% ethanol, so you have 40% ethanol. But what is the remaining 60%? What is the remaining 60%? It is usually water and some flavor molecules, right? So let's just say it is just water and ethanol. So when you're buying a 40% alcohol bottle, it has 40% by volume ethanol and 60% by volume water. Okay, so what would be the solvent in this solution? What would be the solvent? Of course, the solvent is going to be water. Why? Because in this alcohol bottle, you have 60% water, which means you have more water than ethanol. So therefore, water will be your solvent and ethanol will be your solute. So basically, uh, the component that is present in a much larger amount is known as the solvent, and then solute present in a smaller amount. And also you can have more than one solute. Okay, and in this slide I have given you more details about solutes. Okay, so solutes could be liquids, gases, or solids. Okay, they could have any physical state. You can have solutes that could be liquids, gases, or solids. Okay, and they are spread evenly through the solution, as I mentioned earlier, because you have to have an even or homogeneous mixture in order to have a solution. Okay, and then you cannot separate the solvent and the solutes by using simple filtration techniques. Okay, so once you have, let's say, a soda bottle, let's say a commercially available soda bottle, by filtration you can't separate water from the other solutes, such as what, carbon dioxide or flavor molecules or sugar molecules. Okay, so commercial soda is usually what, carbon dioxide or carbonated water with some flavor molecules and some sugar molecules, right? So by simple filtration you are not going to be able to separate those components. Okay, and sometimes these solutes could give a color to the solution. Okay, sometimes these solutes could give a color to a solution. And here I have an example in this image, in this uh, figure. I have an example for copper sulfate solution. Okay, copper sulfate solution. So which means, you know, copper sulfate was dissolved in water. So water is the solvent, and copper sulfate is the solute. Okay, and then what you do is you take some copper sulfate solids, okay, crystals, and then you mix it with water, and then you will get this evenly distributed blue color copper 2 sulfate solution. Okay, so this is an example for a copper 2 sulfate solution. So in here the solvent is of course water, because it is the major component, and then the minor component is copper sulfate. Okay, copper sulfate. Here are some types of solutes and solvents that you could find in nature. Okay, in nature. So once again, guys, it is important to note that you can have different types of solutions in either gas phase, liquid phase, or solid phase. But of course, most common solutions are actually in liquid phase. Okay, so liquid solutions are actually more common. Okay, and most people think that, okay, so if it is a solution, it has to be solid. I mean, it has to be liquid. It doesn't have to be liquid, but liquid solutions are more common as compared to gas solutions or solid solutions. So I recommend that you guys study this table, and as you can see, in a solution, a primary component is going to be your solvent, and then in that solvent the minor components will be your solutes. Okay, and out of the solutes you may have a primary solute. Okay, and then you might have minor solutes, but of course, you know, the primary component is going to be your solvent, and then the rest of the components are going to be your solutes. Okay, all right. So in nature, okay, on earth, the most common solvent that you can find is water. Okay, the most common solvent that you can find is water. I mean, if you remember our previous videos, I mean, we usually, I mean, whenever we write chemical formulas in a chemical equation, we write the physical state called aqueous. If you remember that, I mean, aqueous means, you know, that compound is in a water solution. Okay, so that means solvent is water. Okay, so water is actually the most common solvent for us. Why? Because, I mean, we have a lot of water on earth. Okay, so water is the most common solvent in nature, at least on earth. Okay, and also, it is not that it is very common in nature. It also have some certain physical properties that makes water a really good solvent. Okay, so water consists of some certain physical properties that makes water a really good solvent. So let's take a look at these physical properties. The most important physical property is that water is a polar molecule. Okay, it is actually an extremely polar molecule. It is one of the most polar molecules that you could find. Okay, so water is a polar molecule. Why? Because it contains one, I mean, there are two reasons why water is polar. Okay, the first reason is that water has oxygen atoms and hydrogen atoms, or in other words, you have one oxygen atom and two hydrogen atoms. And of course, oxygen is the second best electron thief in the periodic table, or in other words, oxygen has the second highest electronegativity, right? So oxygen is directly bound to hydrogens, so the electronegativity difference between oxygen and hydrogen is very high. Okay, the electronegativity difference between oxygen and hydrogen is very high. Okay, and therefore this OH bond is a polar bond. This OH bond is actually a polar bond. Oxygen will have a partially negative charge, and the hydrogen will have a partially positive charge. Okay, so you have two OH bonds, so therefore oxygen pole will be partially negative, and the hydrogen side will be partially positive. And the other thing is shape. Okay, so water has a bent shape. If you remember shapes, okay, we learned that water has a bent shape. Okay, so therefore, because of these two reasons, okay, water molecule tend to be polar. And because of this polarity, water is an extremely desirable solvent. And not only that, water has the capability to form hydrogen bonds among water molecules as well as between water and other uh, molecules. Okay, so primary ways of attractions for water molecules are hydrogen bonds. So if you remember, excuse me. So if you remember why water, I mean, what are hydrogen bonds? Hydrogen bonds are intermolecular interactions. And they are the strongest intermolecular interactions, right? So hydrogen bonds are very strong interactions. So therefore, when you can form very strong interactions between each other, okay, you're going to mix with many other molecules. Okay. So the ability of water to make hydrogen bonds, okay, uh, the ability of water to make hydrogen bonds, okay, is very important when it comes to water being a good solvent. Okay, so if you remember what are hydrogen bonds, they are basically permanent dipole interactions between let's say OH, NH, or FH. Okay, these are the three most polar bonds that you could find. Okay, so it will have a negative pole on the oxygen, nitrogen, or fluorines end, and then hydrogen will be partially positive. Okay, and then this polar bond will interact with another, let's say oxygen, nitrogen, or a fluorine. Okay, and this interaction will be very strong because of the polarity of the OH bond or NH bond or FH bond. Okay, so these are hydrogen bonds. Okay, so because of hydrogen bonds, water is very important as a solvent. All right, so let's talk about formation of solutions. Okay, in a solution, you have to have all the components homogeneously distributed. Okay, so if you see two layers, once you mix two solutes or two components or two chemicals, that is not a solution. Okay, so all these three examples that you have in this figure are not solutions. Why? Because you can clearly see two separate layers. So you can't have layers if you have a solution. Okay, so basically solutions form when solute-solvent interactions are large enough to overcome solute-solute and solvent-solvent interactions. So basically, to have solutions, you have to have really good interactions between solute and solvent. Okay, you have to have really good interactions between solute and solvents. Otherwise, you're going to have a solute layer and a solvent layer, which is not a solution. Okay, so the key here to have a solution is to have good interactions between solute molecules and solvent molecules. Okay, so therefore solutions are made up by dissolving likes, or in other words we can say like dissolves like. Okay, which means if the solute and solvent can have similar interactions, they are going to like each other. In other words, if you have a polar solute and a polar solvent, they can of course have uh, dipole interactions, right? So polar solutes are capable of forming dipole interactions, and solvents are capable of forming dipole interactions. So therefore they will like each other. So nonpolar solutes and solvents will also like each other. Why? Because they will have non-polar interactions. But if you have a solute and a solvent with opposite interactions, like polar solutes and non-polar solvents, then they will not mix because they don't interact the same way. It is like, polarity or interactions are like, speaking a language. Let's say, in a room you have two people that speaks the same language. then they mix with each other, they blend, okay, they talk to each other. But if you have two people who don't understand what they're talking about, and they speak completely two different languages, it is hard for them to mix, okay, it is hard for them to mix. So basically the language is what is the interaction form for two people, right? So for solutions you have to have molecular interactions, okay. If you have similar interactions, you are going to interact. If not, you are not, you are going to stay as two different layers. All right, so our next discussion is going to be solutions with ionic solutes, okay. So usually to have ionic solutes, you have to have ionic compounds, okay. So let's take an example, okay. So in here we are going to talk about sodium chloride crystals, okay, salt crystals, this dissolution in water. As you all know, you can easily dissolve table salt or sodium chloride in water, right? So in the beginning, what you have is solid sodium chloride. You have crystalline sodium chloride. But when you put it in water and after stirring it, what happens is that NaCl, the ionic compound NaCl, will separate into cations and anions. Okay, ionic compound sodium chloride will separate into cations and anions. Why? By forming hydrated ions with water. It is like this. Okay, so as we just learned, or from your understanding, water is a polar molecule. You have a negative pole on the oxygen side and a positive pole on the hydrogen side. Okay, so this is how water looks like. You have a negative pole on the oxygen side, a positive pole on the hydrogen side. Okay, and then when this is in when you have sodium chloride in water, okay, sodium is what? Sodium is a positively charged ion. Okay, so sodium is a positively charged ion. So basically, if water wants to interact with sodium, water will have to show the negative side to sodium, right? So basically oxygens, the red color atom, which is the oxygen, so oxygen will basically interact with sodium. Why? Because oxygen has the negative pole and it will interact with sodium. So not only they will interact, they will treat sodium like a celebrity, okay, which means they will wrap around sodium from the oxygen side. So we say that it forms a hydration sphere for sodium. Similar thing happens to chloride, but chloride is a negatively charged ion, and hydrogen will interact with chloride with the hydrogen side. Okay, water will interact with chloride from the hydrogen side. Why? Because hydrogen is positive, so you know positives and negatives are attracted. So basically chloride will be forming a hydrated ion with water, and chloride will interact mostly with the hydrogen pole in water molecule. Once again, it will treat chloride ion like a celebrity, okay. So in the beginning, sodium and chloride are really attracted to each other because of the ionic bond. But in water, okay, water molecules treat both sodium ions and chloride ions really well. Rather than staying together, sodium chloride will grow apart, okay, and make hydrated ions. So therefore sodium ions and chloride ions will be separate ions. I hope it is clear to you, okay. So sodium chloride will no longer be a crystal in water. Sodium and chloride ions will make hydrated ions, and therefore they will be separate from each other. And of course, because of that, they will make a nice solution with water. Okay, sometimes, okay, if you have polar solutes, like ethanol in this example, okay, or methanol in this example. So polar solutes like alcohol, methanol, okay, will also interact easily with water. Okay, will also interact easily with water. If you take a look at this alcohol molecule methanol, okay, it has this OH group. It has an R group, which is hydrophobic, by the way. Carbon hydrogen groups are hydrophobic. They don't like water. Why? Because they don't have similar interactions with water. So let's call it R. But look at the OH group. It resembles the OH group of water. And the oxygen pole will be partially negative, hydrogen pole will be partially positive. So this OH group on alcohol can easily interact with water molecules. Why? Because water also has a negative pole on oxygen, and a positive pole on hydrogen. Okay, so the negative poles and the positive poles on water and OH will easily interact, and then those interactions are not only regular interactions, they are hydrogen bonds, so they will easily form very stable interactions between each other, and therefore they will make a nice solution. Okay, nice solution. That is why when you buy an alcohol bottle, in alcohol you have ethanol, not methanol. Methanol is toxic. You can't drink it. If you drink, you die. Okay, so but usually these small alcohols like methanol and ethanol, they will form hydrogen bonds with water. Okay, that is one of the most strongest interactions that you can have, and because of that, they are going to be soluble in water. So when you buy an alcohol bottle, okay, you don't see two layers in the alcohol bottle. Instead, it is just one layer, right? One layer, and it is homogeneously distributed. Okay, it is homogeneously distributed. So that is how it happens, guys. That is how it happens. Okay, so let's go to the next slide. Okay, I have a small study check here. All right, see if you could do this. You might want to pause the video and try them before I go through them. Okay. All right, in this study check, I want you to identify the solute in each of the following solutions. Okay, so let's do this. A, you have 2 grams of sugar in 100 milliliters of water. Of course, 100 milliliters of water means you have 100 grams of water. Why? Because each milliliter of water is 1 gram, okay? So you have 2 grams of sugar and 100 grams of water. So of course, water is the overwhelming majority in this solution. So therefore, water will be your solvent, and therefore sugar will be your solute, the minor component. In B, you have ethyl alcohol and methyl alcohol. The minor component is methyl alcohol or methanol, so therefore that will be your solute. In the next example, you have 55 grams of water and 1.5 grams of sodium chloride. So sodium chloride will be your solute, the minor component. In air, you have 200 milliliters of oxygen and 800 milliliters of nitrogen. So the minor component is oxygen, so that will be your solute. Okay, that will be your solute. So that is an easy study check. Let's do another one. Okay, so in here, once again, try to pause the video and try it before I explain it. Okay, when solid lithium chloride is added to water, it dissolves in water. Why? Because lithium ions are attracted to the negative pole or the oxygen atom of water. So the correct answer is 1. Okay, chloride ions are attracted to water. Chlorides are negative, so you need to have a positive pole. So positive pole of water, which are hydrogen atoms. All right, now you know. Here's another study check. Which of the following solutes will dissolve in water and why? First compound, we have sodium sulfate. Is sodium sulfate soluble in water? Of course it is soluble in water. Why? Because one, it is an ionic compound. Okay, it is an ionic compound, but here's the thing. Just because, a compound is ionic doesn't mean that it is going to be soluble in water. Okay, calcium carbonate, okay, is also an ionic compound, but calcium carbonate is not soluble in water. In sodium sulfate, you have sodium ions. Okay, the thing about sodium ions is that they really like water. So sodium ions always tend to form sodium ions in water. okay, aqueous sodium ions, okay. So therefore sodium sulfate is soluble. So sodium sulfate is soluble. Why? One, it is an ionic compound. Two, that ionic compound also has sodium, which really likes to be in water. Okay. All right. B, gasoline. Okay, it says that gasoline is a non-polar compound. Water is a polar compound. So no, it will not interact with each other. It is like, two different people that have nothing in common. Gasoline is non-polar, water is polar. Polar and non-polar, they don't mix. Okay, so you will not have a solution. I2, once again, I2 is a non-polar molecule. Why? Because you have two iodines connected to each other. When you attach to your own kind, the electronegativity difference is what? END is 0, which means there is no electronegativity difference between each other, so you can't steal from the other guy. You can't attract the bonding electrons. Okay, so therefore there is no polarization. So iodine will not be soluble in water. It is very hard to get it into water. Okay, so no, it is not soluble in water. HCl. HCl is a polar molecule. HCl is a polar molecule. Okay, so HCl is a polar molecule. How do you know that? Chloride has a high electronegativity and hydrogen has an average electronegativity. If I remember, chloride has I don't remember the electronegativity values exactly, but chloride has a very high electronegativity, or you can say the third highest. Yeah, third highest electronegativity, and hydrogen is 2.1. So the electronegativity difference is very high, so they will easily go into water. Not only HCl goes into water, it will actually ionize. Okay, it will ionize, forming H plus ions and chloride ions. Okay, so A and D will go into water or dissolve with water. All right, guys. So our next discussion is going to be on electrolytes and non-electrolytes. Okay, this discussion is extremely important, especially for nursing students. Okay, for nursing students or students who want to go into health science, because you're going to deal with a lot of electrolytes and non-electrolytes. Okay, so especially in our body, electrolytes have a very important role. Okay, they basically help us in doing many popular functions. Okay, so let's talk about them. Okay, let's talk about these electrolytes. Okay, so electrolytes can be separated into three. Okay, strong electrolytes, weak electrolytes, and non-electrolytes. Okay, strong electrolytes, weak electrolytes, and non-electrolytes. So the difference between these three categories is when you have a chemical compound in water, okay, like sodium chloride for an example, how well you ionize, or in other words, how well you dissociate, okay, in water. So if you have a chemical compound that dissociates 100% in water, if you have a chemical compound that dissociate 100% in water, okay, that means forming negative ions and positive ions in water, that compound or the solution is known as a strong electrolyte. Okay, that solution is known as a strong electrolyte. So when you have salt, NaCl, in water, when you have sodium chloride in water, that is a strong electrolyte solution. Okay, so if you couldn't find a strong electrolytic solution, you can put some salt into water and then you can use it as a strong electrolyte. Okay, so NaCl dissociate completely in water. And here is a simple experiment. Okay, so basically if you have a sodium chloride solution, it has sodium ions and chloride ions, okay, at high concentrations, and when you have ions in water, they can easily conduct electricity, right? So in this beaker, okay, what you have is a sodium chloride solution, and then sodium chloride ions will help transport electrons from one electrode to the other. Okay, that is why this bulb is illuminating. You have plenty of ions in water in the form of sodium and chloride ions, so they can easily uh, uh, they can easily transport electrons from one electrode to the other. Okay, so therefore if you have a strong electrolyte, this bulb will illuminate. Okay, this bulb will illuminate easily. The next solution we are going to talk about is called electrolytes. Weak electrolytes. Okay, here's the thing: weak electrolytes will also dissociate, but not fully. Okay, they will only partially dissociate in water. Things like weak acids and bases. Okay, they don't fully dissociate in water. Instead, they will dissociate partially. Okay, if you take hydrogen fluoride, HF, as an example, in water, it will partially break into H plus and fluoride ions, which means only a few percent, like less than 10% in this case, if I remember. Yeah. So since you are only partially dissociating, uh, you only have a few ions as compared to like the previous strong electrolyte example. So therefore, if you want to transport electricity in this figure, okay, you only have a few ions. So therefore, you will not get an intense illumination like before. Okay, like before. The third solution that we are going to talk about is non-electrolytes. Okay, so non-electrolytes do not have ions in water. But in here you will have molecules that are soluble in water, or they will dissolve easily in water, like sucrose, which is a sugar. Okay, so it will easily be soluble in water. But here's the thing: it will be soluble, but it will not form two different ions, or cations and anions in water. So therefore, you will have aqueous solutions of those molecules, but no ions. If you don't have ions, there is no way to conduct electricity. So therefore, this bulb will not light up. Okay, so non-electrolytes have molecules that are soluble in water, but they will not produce ions in water. So therefore, there is no conduction of electricity. Okay, all right. So here is a nice table that basically summarizes what we discussed. Okay, once again, guys, if you want to have a strong electrolyte solution, you have to have a chemical compound that will dissociate fully in water, like strong acids, strong bases, or salts that are fully dissociate in water. Weak electrolytes are usually weak acids or weak bases. They only partially dissociate in water. Okay, non-electrolytes, they do not dissociate at all. Okay, they are just soluble in water, but that is it. All right. Okay, so let's quickly do this study check. Okay, complete each of the reaction for strong electrolytes in water. Okay, all right, so try this by yourself first and then see if you could do it correctly. Okay, so you have calcium chloride, which is a strong electrolyte, of course, and then it will dissociate into a calcium ion and two chloride ions. So the correct answer will be C. And then in the second question, I have potassium phosphate. So in water, it will dissociate into potassium and phosphate. Okay, so the correct answer is actually A. Okay, A. This is the correct answer. If you pick C, that is wrong. Okay, in here phosphate is a polyatomic ion. Okay, so it is PO4 3 minus. This is phosphate. Okay, and calcium is K plus. Okay, so don't pick C. All right, guys, so that is how you do this study check. Okay, which of the following in the next study check, which of the following reactions represent the dissociation of a strong electrolyte in water? Okay, this is where you will pause the video and try it for yourself. A, it is not forming any ions, right? So in this case, you are making ammonium hydroxide and it will dissociate partially, so it is not a strong electrolyte. B, you have liquid methanol in water will become aqueous methanol and it will not dissociate. Even if it dissociate, it will be a very weak dissociation. Okay, so it will not be a strong electrolyte. But sodium sulfate, yeah, that will completely dissociate in water. So this will be a strong electrolyte. Okay, and then you have methanol in water. Once again, aqueous methanol might dissociate ever so slightly, but that is not a strong electrolyte. Okay, that is not a strong electrolyte. So the answer is C. All right, see if you could do this study check by yourself. Write the equation for the formation of a solution for each of the following. All right, so basically, excuse me. So in A, what you have is potassium chromate. What you have is potassium chromate, which is a strong electrolyte, by the way. How do you know that? It is an ionic compound. That is the first thing. And also potassium, oh, there should not be 2 minus on it. Okay, and also potassium ion really likes to be in water. Okay, it really likes to be in water. So that is why this will go into water easily. Okay, so if you add water into this one, you will get 2 potassium ions, and then you will get 1 chromate ion. This is the equation. And next you have phosphoric acid. Okay, so here's the thing, phosphoric acid is a weak acid. Okay, phosphoric acid is a weak acid, so you'll have H3PO4. From that, it will show partial dissociation. Okay, so you will have some H plus and then HPO4 minus. Okay, remember to use the reversible arrow because it is not a strong acid. If phosphoric acid is like HCl, then you will have complete dissociation. Okay, all right, so then the next one that we have is sugar. So this is an easy one. Okay, so sugar is soluble in water, but it will not dissociate in water. Okay, so here is your sugar. In water it will be aqueous sugar. Okay, aqueous sugar. So with that, I'm going to conclude this video. Okay, so I hope that you guys understand what are solutions and electrolytes now. Okay, let me know if you have any questions. Okay, you guys have a good one. Take care.